the previous lecture, we had looked at the finite element method, and we had done a simple implementation of that method using the hat shaped functions or the linear functions to a problem of a bar. So, if I can draw that problem again, this is the bar with an end load P and subjected to a uniformly distributed load F0. So, in that case, we had built up the element equations, we had introduced the idea of element calculations, and then we had discussed how to take these element equations and put them in the global matrices, that is the global stiffness matrix K and the global load vector F. How the element calculations, which we had written as K of L, element L, and the matrix and the load vector from the element F due to the element L. How these equations will be put in these global equations in terms of the K and F. And we had said that this will lead to finally, after assembly, an equation of this form Ku equal to F. Now, what we had done in the last class is we had developed this matrix K, we had developed this vector F, but we had not taken into account the effect of the boundary conditions. Now, how do we account for the boundary conditions? We had taken care of this end force P here by saying that if we consider the domain is broken into 6 elements, as we had done, into 5 elements, 3, 4, with nodes x1, x2, x3, x4, x5, x6, x6 is equal to L and x1 is equal to 0. Then we had said that for in the entry F6, we updated it equal to F6 plus P. That is, in the final entry of the vector F, we added the value of this end load P, which is applied. And why we did it was discussed in the last class. So, this part was taken care of. What we had left at is a little bit more complicated part of application of boundary conditions, which is how do we impose the Dirichlet or the essential boundary conditions. This is where we had trailed off in the last lecture. So, what do we have for our problem? We know that for our problem, U6 is the approximation that we have made. This is equal to sum of I equal to 1 to 6 ui phi ix, and we know that u6 at 0 for this problem has to be equal to 0. Now, at x equal to 0, which is the node x1, only phi 1 is equal to 1, all other phi's are 0. So, this is equal to u1. So, this condition has to be explicitly imposed in the solution. So, how do we explicitly impose it? So, let us go to the system equations that we have. So, if you remember, what was our global stiffness matrix? So, let us start with the system equations as we had written. So, what did we have earlier? So, I will write it in a little bit general way. So, our first equation was minus Ea by H1, sorry, plus Ea by H1 minus Ea by H1 and 0, 0, 0, 0. Second one was minus EA by H1. Here I will get, because of the assembly, EA by H1 plus EA by H2. Third one will be minus EA by H2 0 0 0. Okay. This way I will continue till the sixth equation. Which is 0 0 0 0 minus EA by H5, and here I will have plus EA by H5. So this was our global matrix K. So if this is our global matrix K, this into the U was equal to the F. So now here you see that nowhere have we really taken care of the value of U1. That is, we have not imposed the fact that the value of U1 has to be equal to the specified value. Let us now be a little bit further general. We will say that U at 0 is given the value U0 bar. So from what we have done earlier, this will be equal to U1. So how do we impose this in our solution? So the idea is very simple. We will take the first equation. So I will take the first equation, and what will I do is I will replace this guy with 1. The first entry, that is the diagonal entry corresponding to the first row, that I am going to make as 1. The second entry I am going to set to 0. That is, all other entries in this row, the first row corresponds to U1. So the diagonal entry of the first row I am going to make it 1. All other entries I am going to make it equal to 0. At the same time, what am I going to do to the F1? I am going to put F1 is equal to U0 bar. Just look at the first equation. So in the first equation, what do we end up getting? So the first equation becomes 1 into U1 is equal to U0 bar. So this, by modifying the first row of the first equation, I have first row of the stiffness matrix, I have enforced the fact that U1 has to come out to be equal to U0 bar. Now the question is that when we enforce this, the other equations have to change also. So if I go back to my previous equation, so you see that the second equation, in the second equation, this is the part corresponding to U1, right? This is the entry in the second equation corresponding to U1. Now we know that U1 is equal to U0 bar. So how do we remove this from this side and put it into the known part? Because U1 is equal to U0 bar, which is known. So the idea is very simple. So what we do next is, we will, for all other equations, we will put, that is for I equal to 2 and more, we will put Fi is equal to the original Fi plus or minus, sorry, it will be minus K. Which entry are we looking for? The entry corresponding to the U1 in that particular equation. So that entry will be, so the row will be I, column will be 1 into U0 bar. So this is how we are going to modify our load vectors. So you see, what happens in our case is that for all other entries below, so for the second equation, this has to be taken care of because this entry is not equal to 0. But from the third to the sixth equations, U1 does not figure in the equation. So trivially nothing has to be done because it is 0 which is being added or subtracted from the right hand side. So with that in mind, now what do we have as our second equation? So, modified f2 will be equal to, by this token, what we had earlier as our f2, okay, minus of, we had k I1, that is the first column of the second row we want to take. So, it will be minus of EA by H1 U naught bar. So, this will become the modified right hand side for the second equation. Okay. So, let us rewrite it. So, this will be equal to, what did we have as our f2? f2 was f naught by 2 into H1 plus H2. So, to that I am going to add EA U naught bar by H1. So, this becomes the so called corrected or the modified right hand side for our problem. So, once we have this, so now what do we do? Once we have transferred this information to the right hand side, then after we have done that, then we are going to set k I1 is equal to 0. That is, we are going to blank out all the entries in the first column for all the rows. This is for I equal to 2 to, for our problem 6. Certainly, we are not going to do this to the first row, because then it makes no sense. From the first row, we want U1 is equal to U naught bar, and from the second row onwards, we want to take care of this known value of U naught by suitably modifying our load vector. So, if I now use this and write the system, I will end up getting the system. I will call it k modified into the displacement vector u is equal to the f modified. So, once I have these two things, then I can solve for u. Now, how do I solve for u? I can solve for u by taking the inverse of k. So, it will be u will be equal to km inverse into fm. Now, here we are not going to talk too much about what kind of solvers. What I would request the students to do is to go use some commercially available code. For example, you can use MATLAB or Mathematica. To solve this problem, that is, you can feed to these programs the matrix K, the vector F, and ask it to return back to you the vector U. So, once you know the components of U, then you know your solution U6, because this will be equal to ui phi ix. So, this is how we will construct the finite element solution to a problem. Now, the question arises that, okay, why did we not ignore the first equation right away? Because the first equation was meaningless from our point of view, because we completely changed it. That is the first row, because u1 was known to us. Now, we have to remember that when we are developing a method, it has to be a general purpose approach. This was a particular example we took for which we had said u1 is a known value. For example, for our problem, u1 was actually equal to 0. So, really these corrections that we did as far as the load vector entries are concerned were also trivially equal to 0, the correction terms. But we anyway did it to show that in case u1 is a non-zero number, which could be the boundary value problem corresponding to a boundary value problem of interest. that is, I fix one end to a given deflection. That is also possible. So in that case, what is it that we have to do? And you see that this general purpose approach gave us the right way of doing things, out of which the special cases will also come out as the solutions. So remember that whenever we are developing anything, we have to have the generality of the approach in mind. So with that in mind, we have done all these things. Now another reason why we should assemble the first equation also is seen from the next example. Let us take a simple problem which is like this. So this is again a simple modification of our earlier problem. This is a bar with distributed load F0 and end load of size P at the point x equal to L, and at the point x equal to 0 I apply a load Q, and this is a static problem. So we know that for a static problem, static equilibrium for the whole component has to be satisfied. So out of that, we know that the P and Q cannot be arbitrary. That is, if I give F0 and P, I know what Q should be for the system to be in static equilibrium. So looking at that, what is our Q? Q is equal to P plus F0 L, because in this case our F0 is constant intensity distributed load. Okay, this we will call as the so-called consistency condition. That is, the load has to be consistent to give us static equilibrium. Okay, now for this problem, what do we do? Remember that for this problem, we have already formed the stiffness matrix for the mesh of 5 elements. So let us keep that mesh of 5 elements. Okay, such that again here my mesh size HL is equal to H, which is L by 5. Okay. So for this 5 element mesh, we already know the stiffness matrix, that is the unmodified stiffness matrix. So that we will inherit from what we had done earlier. So the K stays as what we had obtained for the previous problem before we applied the boundary conditions. So this will be equal to, if I remember it correctly, it is EA by H into 1 minus 1 0 0 0 0 minus 1 2 minus 1 0 0 0 0 minus 1 minus 1, then finally you will get 0 0 0 minus 1 2. This is the matrix K. What is my F? F, as we had said, the unmodified F, that is before applying the boundary condition. So I will write the transpose of F so that things are easily written. So 1 2 3 4. Now comes the next part, that is we have to take care of. If you remember how we went about this thing is, after we got the unmodified stiffness matrix and the load vector, then we took care of the Neumann boundary conditions first. Now in this problem, both ends have Neumann boundary conditions. So if I look at the weak form, you should remember the weak form also. It is integral of 0 to L EA u prime v prime dx is equal to integral 0 to L f naught v dx plus you have EA du dx v evaluated at L minus I have EA du dx v evaluated at 0. Now, the question is, what is EA du dx at the two ends? So, at the two ends, at x equal to L, EA du dx is P. At the end, x equal to 0, this is equal to Q. So, let us go and look at it in greater detail. So, from 0 to L, we have EA u prime v prime dx. This is equal to 0 to L f naught v dx plus P v evaluated at L minus Q v evaluated at 0. Now, I would like to ask this question, that which of the v's, because we have chosen our v to be the functions phi I, which of the v's will be 1 at point x equal to 0 and 0 at the point x equal to L. So, that is, I would like to know which v will be non-zero here, and by now we should know that this will be equal to phi 1 evaluated at the point 0, which is equal to 1. V at L, which of the phis is non-zero at the point x equal to L? So, this is phi 6 at L, this is equal to 1. So, from this what do we see? That if I look at the equations, put v equal to phi I, then this P has to contribute to the load vector term corresponding to phi 6, and Q has to contribute to the load vector corresponding to phi 1. So, what do we do? So, here we apply the Neumann conditions. So, what do we do? To the known F1 that we have computed using this part, to that we are going to add or subtract, because Q is given like that, Q. So, this will be now the modified F1, and just like what we did earlier, F6 will be equal to the computed assembled F6 plus P. So, application of the Neumann boundary conditions for this one dimensional problem is very easy. That is, you go to the corresponding rows and just add a number, because Q is a number, P is a number. Now, once we have this, what do we know about V for this problem? In this problem, V is unconstrained. What does that mean? So, let us see what this will relate to. So, remember that there is no geometric constraint to be imposed. So, we take the original K that we got out of assembly, keep it, and this will be the load vector will be modified, one which we obtained by the previous step. Now, the question is, if I want to solve this problem, can I solve? That is, I have to find K inverse. Before we find that, we have to know whether it exists or not. So, what do you think, whether K inverse will exist or not? You remember that V is an unconstrained test function. So, if it is an unconstrained test function, then I can very well use Vx equal to 1. That is valid. Why is it valid? Because it satisfies all the conditions or the constraints that we have put on V, that is, the derivative of V exists, the energy due to V is finite, it is 0 actually. So, we can use this. Vx is equal to 1 everywhere. Now if we put it back in our weak form, what do we get? So integral 0 to L Ea u prime v prime dx becomes equal to 0, and this on the right hand side will be equal to integral of f naught v, so it will be f0 L plus p minus q. So what do we see? That we had earlier stated the consistency requirement for static equilibrium, and that has come out of this also, that this is what we want our loads to do. Our loads have to satisfy this constraint in order to find a solution to the problem. That is for K inverse. K inverse we'll see whether it is invertible or not, but at least here the issue is whether we can solution can be found or not. So the next question is, okay, what can we say about K? So you see one very curious thing, that if I take the unmodified K and I choose u to be equal to the vector 1 1 1 1 1 1 transpose, then what is Ku? So I will call it u choice. Kuc will be equal to 0. It will be equal to the 0 vector. Then what can we say about uc? Uc is essentially the vector which lies in the null space of A. That is, for certain there is one vector for which, one non-trivial vector uc for which Kuc is equal to 0, which means that certainly K has a rank deficiency of 1. Okay, so K has certainly a rank deficiency of 1. The question is there more? That is, are there any other vectors which are not the same as uc and which are non-trivial for which Ku is equal to 0? The answer is no. There are no other vectors which are different from uc. That is, you can multiply uc with a constant, that does not change the vector as such. So excepting uc, there is no other vector for which Kuc is equal to 0. So K has a rank deficiency of 1. This is fine from mathematics. From physics, what does this mean? It means that for rigid translations, which means that if my u of x is equal to some constant, that is, the whole bar is moving as an entity, in that case the stress and the strain at any point in the bar are 0, because it's a rigid body motion. There is no relative deformation of one point on the bar with respect to the other point on the bar. So if there is no relative deformation, there is no strain. If there is no strain, there is no stress. Okay, so the rigid translations correspond to 0 strain energy for the system, which is what we got. So the 0 strain energy modes are the rigid modes, and for this bar, this is the only mode which is there, and this shows in the rank deficiency of our system. That is, there is no other rigid motion which is permitted for this kind of a bar. So the rank deficiency of the stiffness matrix that we got is 1. Okay, so now question is, find the rank deficiency is 1, and we saw that our system equations are consistent, so solution will exist. But the question is, here we will have infinite solutions. Okay, because so many solutions are available. What do we mean by that? Infinite solutions which will be of the form ux is equal to, I will call it u deformation of x plus u rigid of x, that is plus c. That is, the second part corresponds to the rigid translation, and it could be anything, a constant c, and this part is the one which leads to non-zero stresses and strains in the bar. So what we want is, see, really we are interested out of this problem in knowing the state of stress and the strain. Stresses and strains will require derivatives. So if you look at this, du dx will be equal to du d dx plus 0. That is, the rigid part does not contribute to the derivative. So if the rigid part does not contribute to the derivative, that is, its presence does not change the strain information, then I can fix this c to be anything and get the same derivative or the strain. So we will put c equal to 0. We can put, okay, c equal to 0 means that your u rigid is 0. Now if u rigid is 0, we can say that, how do we enforce this in our problem? We can say, fine, I am going to say that ux at point 0 is equal to 0. I can enforce this also to fix the rigid motion, okay, which is equal to the u1. So once I do this, then I will follow the same route as we followed in applying the Dirichlet condition to get a solution. To the problem. Okay. So we are fixing ux at the point 0 equal to 0. It is not the same as putting c equal to 0, such that we get a solution to the problem. And how do we impose this in our code? It is by modifying the equation corresponding to u1, that is, k11 we are going to make equal to 1, k1i for all i's greater than 1 we are going to make equal to 0, and similarly ki1 is equal to 0 for all i's. So under this condition we are going to get a solution to the problem. Okay. So you see that there was a very important issue that we have tackled here, that is, a solution to a problem may not exist. That is, if I apply the loads wrongly or if I apply my boundary conditions wrongly, I will get garbage solution. So let us look at another problem which has a little different boundary condition. So what do? Let's go to the next problem. Since we are playing with problems, so let's do this one, that here is a bar. Again, let us keep it to f0, but here what I do is, at this end I fix a spring with spring constant k, and what do? I give an initial compression to the spring delta 0. So this is the point x equal to 0, this is the point x equal to L. So if I give this initial compression delta 0, then due to the action of this force, this bar is going to elongate, that is, the end x equal to L will move by an amount u at L, right, due to the action of the forces. So which u of L is unknown. So now for this u of L that you get at this end, what is the total force that the spring is applying on the bar? the spring applies a compressive force of size K into delta naught plus U at L, right, because the total compression of the spring now becomes delta naught plus the displacement of the end L, which is U at L. So now in our formulations that we have done, let us write the weak form for this problem. You should always write the weak form to the particular problem that you are trying to solve to understand what is going on. So weak form will be integral x is equal to 0 to L f naught v dx plus P at the, that is the applied external force at the end x equal to L into V at the end x equal to L. Now what is this force equal to for us? It is actually, if you remember, the P was tensile earlier, now it is compressive, so it is minus P. So this plus becomes actually a minus. So I will write minus K delta naught plus U at L multiplied by V at L. So this is the weak form we get. Now you see there is something very curious about this weak form. This unknown UL, we had said that in the weak form we are going to collect the unknowns on the left hand side and the knowns on the right hand side. But you see that in the right hand side now even an unknown UL is sitting. So what do? We shift it to the left hand side. So when we shift it to the left hand side, the weak form becomes to L EA U prime V prime dx plus K U at L V at L is equal to integral 0 to L f naught V dx minus K delta naught into V at L. So with this, what happens? Now let us go to our finite element formulation. Let us again take the 5 element mesh, okay, that we had drawn. For the 5 element mesh, now tell me what is it that we have to do with respect to the application of these conditions. So first thing that we do is we ignore these two terms and we do the standard element calculations to find the element matrices KL and FL, assemble them into the global matrix K and the global vector F. Now you see that this condition KUL VL will be something that we have to apply to the stiffness side. So tell me in the stiffness for which phi, that is for which rho this part is going to cause a change. V at L, which V is non-zero at L? So this is true for only for us the phi 6. So V at L is equal to phi 6, that is for the sixth equation. We will have to modify the stiffness term. Now for which, this is the rho which is fixed, so now for which column? The column comes out of the UL that we have. So U at L, if you remember, what is the representation for U? It is sigma Ui phi I. So which of the phi i's is non-zero at x equal to L? It is again phi 6. So this will be essentially U at L will be equal to U6 phi 6 at L. Now what does this lead to? So this whole thing, this whole expression, if I want to write it somewhere, this will become K U6. Okay. So this tells me very clearly which column this has to go in. So this means this entry goes into the sixth column. Okay. So in the stiffness matrix that we have obtained out of our assembly, we go and add k, because u6 stays in the vector, the displacement vector. So I will add k in the 6th column of the 6th equation. So that is the first thing we have to do. Second thing, let's see as far as the load. So now this term looks very much like what we have handled as far as the load is concerned. So this is very easy, because V at L is only non-zero for phi 6. Okay. So this minus k delta 0 goes to the 6th load vector. Okay. So let us do that, and then what else do we have to apply? So let's do this thing. So now we will put k 66 is equal to k 66 plus small k. F6 is equal to F6 minus k delta naught. So these give us our modified stiffness matrix K and the modified load vector F. But our job is not yet done, because we have to also put that U1 is equal to 0. So for that we will again make K11 equal to 1, F1 is equal to 0, K1I is equal to Ki1 is equal to 0 for I is equal to 2, 3 up to 6. So once we do this, apply these conditions, then I will get the K modified which is what we have to solve. So you see that here, because of the spring at the end x equal to L, even the stiffness matrix needed a modification. Okay. This kind of boundary condition, which is in terms of a spring applied at one of the ends, is called a mixed BC or a Robin boundary condition, okay, which is that the end load, that is the EA du dx at the point x bar is given in terms of some constant plus beta times u at x bar. That is, the boundary condition is given in terms of some known and a component which is unknown, because u here is unknown. So it's mixed in the sense that it has both the knowns and the unknowns sitting in the boundary condition. And because this unknown u is sitting there, this has to be taken to the left hand side, and it leads to a change in our stiffness matrix. So these were some of the problems that we can handle. But you remember that our basic assembled K and F that we obtained out of assembly they remained unchanged till we came to the next part, where we first applied the force boundary conditions, whichever end it is given, and then we applied the displacement boundary conditions, whichever end it is given, displacement or the even mixed one. Okay. This is the procedure we are going to follow in any finite element computation. And you see, the beauty of it is that out of our element calculations, the stiffness matrix and load vector came out automatically. Now the question is, if I want to change the number of elements in the mesh, no problem. So if I want to change from 6 to, let's say, some number, let's say the total number of elements is NEL, these could be non-uniform. So non-uniform means that the mesh size is not the same for each element, then does it pose any problem? From what we have done, the stiffness matrix for any number of elements, let's say NEL is equal to 100, can be easily formed using the stencil that we have given. And what is the stencil? It is that the equation will have out of the element contributions due to N1 of the element L and N2 of element L. So, the equations for the element remain unchanged irrespective of whether we are using 100 elements or 5 elements. The only thing that changes is the H, that is the mesh size in what we have done, and the material parameters that you may wish to change. Okay? So, the element matrix remains essentially, the representation remains same. Then it is a matter of assembly which we can do. So, now using this approach that we have outlined for this problem, very easily we can form the stiffness matrix and the load vector for a mesh of any number of elements, or with any number of elements with either uniform meshing or non-uniform meshing. Okay? So, once we do that, so we can form the global matrices Ku and F, solve. So, first after we assemble, then we apply the force boundary conditions, then after that we modify the matrices to take care of the displacement boundary conditions and solve the problem. The thing is that the bigger the size of the system, certainly it cannot be solved by hand. So, we have to go to a computer to invert the matrix K. Okay? But in principle, we can easily form this matrix K and solve it. Okay? And then obviously, you have to remember that U here will be equal to, let us say, number of elements plus 1 is equal to sigma I is equal to 1 to NEL plus 1 UI phi I x. So, this U finite element that we have obtained, it can be easily obtained. So, what I would like is, as an exercise, you can take Fu equal to 10, F0 is equal to 10, P is equal to 20, EA is equal to 1, and solve this problem using 2, 4, 8 or 16 elements and so on, elements of uniform mesh size. That is, in this case, your H will be equal to, uniform mesh size means H will be equal to L by N EL, and let us take L is equal to 1. So, one can easily attempt this solution and see that what should you see out of this, that if this is X, this is U. So, let us say this is U exact, then this will be the 2-term solution, 2-element solution, then this will be the 4-term solution, then the 8-term solution. I will make it with blue again. You can see that essentially what will happen, your solution will keep on coming closer and closer to the exact solution, and you see that as the number of elements is increased, your approximation does very well. This is true for any of the boundary conditions you take. Okay? Now, the question is that, do we always have this type of a differential equation to handle? The answer is no. So, let us make this differential equation a little bit more complicated. It will still be a straight bar with an end load P, but here we will have a distributed spring support. So, it is an axial support which leads to a spring constant, a distributed spring constant kx. So, as if the bar is resting on a rubber padding, and this rubber padding is applying a uniform resistance with the force proportional to the displacement, and the proportionality constant is k of x, because it is changing with the position. So, in this case I will simply write the differential equation again. It will be d dx plus k of x u of x f of x. So, this is the differential equation. The boundary conditions we have already stated them. So, the weak form for this problem will be integral x is equal to 0 to L EA, again by doing integration by parts, u prime v prime dx plus integral x is equal to 0 to L k of x u of x v of x dx. This is equal to integral f v x is equal to 0 to L dx plus p v at L. So, this is going to be the weak form of the problem at hand. Okay. Now, the question is, I say that let us do the finite element approximation corresponding to this problem. So, let us again go back to our 5 element mesh. Okay. For this mesh, what is going to change as far as the element calculation is concerned? So, if I take a generic element out, element L, x1 of L, x2 of L, this is n1 of L, n2 of L. So, what is going to change? What we are going to change is that, look at the element level. So, x1 L to x2 L, you are going to evaluate this guy, plus now you are going to evaluate this contribution also. Okay. The load vector side remains the same. So, this part is now an addition. So, for what do we do? So, we replace this, wherever u is there, we will do u is equal to phi I or phi I plus 1, and similarly v is equal to phi I or phi plus 1. So, what will happen is that to our standard element stiffness matrix that we had calculated earlier, we have to add this part corresponding to v equal to phi I or phi I plus 1, similarly u equal to phi I or phi I plus 1. So, all we are going to do is change. So, the k element will be equal to, what do we have if you do this integration? So, earlier we had EA by HL minus EA by HL minus EA by HL, EA by HL, and we had said this corresponds to phi I, this corresponds to phi I plus 1. Similarly, this row corresponds to phi I, this row corresponds to phi I plus 1. To this we are going to add plus, what are we going to add? So, here we are going to add, let us take kx is equal to some fixed value k0. So, we are going to add k0, if I integrate out, into integral x1 of L to x2 of L, okay, n1 of L into n1 of L dx k0 integral x1 of L, x2 of L, n1L, n2L dx, and this will repeat here, and here we will add k0 x1 of L to x2 of L, n2 of L, n2 of L dx. So this additional part, if you work it out, will be equal to k0. I have taken k to be constant, but it need not be. So the additional part becomes k0 into HL by 3, HL by 6, HL by 6, and HL by 3. So this has to be added to the element stiffness matrix that we got out of the first part, and that will give us a total element stiffness matrix K L, which will now become equal to minus plus EA by HL plus K naught HL by 3 minus EA by HL plus K naught HL by 6 minus EA by HL plus K naught HL by 6, here EA by HL plus K naught HL by 3. Okay. So this is all the modification that has to be done to the stiffness matrix. Curiously, in this case, the problem with forces at the two ends will have no problem as far as the solution is concerned, because in this case the global stiffness matrix is invertible because there is no rigid mode. Because if you had a rigid displacement, it would lead to displacement deformation of the springs, so the energy of the system is not going to be 0. Okay. So with this, let us now close our exercise that we did with respect to a very simple finite element formulation using hat functions, and we saw how we construct the element calculations, how we apply the rules of assembly to form the global stiffness matrix and the global load vectors, how we apply the Dirichlet boundary conditions, and first the Neumann boundary conditions, then the Dirichlet boundary conditions, whether we have to check for consistency or not, that has to be problem dependent, and we further extended a problem to include various types of boundary conditions, and also finally the case where there is a distributed spring attached to the member. Okay. In the next class, next lecture onwards, we are going to refine whatever we have done further. That is, we will address the issue of how do we go from this setting to a setting which will be more amenable to a computer implementation, and also how do we address the issue of improving the accuracy of the solution, not only through mesh refinement but also by increasing the order of approximation. Thank you.